Welcome to this explainer. Today, our mission is to capture the absolute essentials of the book Quantum Computing for Dummies, and we're going to do it in 8 minutes or less. We are stripping away the complex jargon to build a clear, structured understanding of a technology that is literally going to reshape our future. The authors took on this massive challenge of taking one of the most mathematically punishing topics in human history and framing it in a way that's actually accessible, and that is exactly what we're going to break down today. To kick things off, I want you to picture flipping a coin high into the air. As it's spinning up there, just suspended in midair, ask yourself, is it showing heads or is it showing tails? If you look closely at it, it's really just a metallic blur, right? From a physical perspective, while it's in rapid motion, it actually exists as a probability of being heads and a probability of being tails at the exact same time. It's occupying both of those states simultaneously. The reality is, you can't possibly know the definite answer while that coin is spinning. It's only when it hits the table and finally settles down that it's forced to display a single definite result. This uncertainty, that blur, perfectly captures the core concept of quantum computing. But instead of coins, we use subatomic processing elements called qubits. Physically, a qubit might be the specific spin of a single electron or the polarization of a photon. We basically put these tiny qubits into a controlled state of uncertainty, effectively spinning the coin. We program them while they're fluid, run our calculations, and then, finally, we measure the result. That act of measuring forces the qubit to mathematically collapse into a definite 0 or 1. The measurement itself is the coin landing. Our authors, Worley and Floyd Smith, jokingly compare this emerging quantum landscape to the hydrothermal vents at the very bottom of the Mariana Trench. It's an extreme environment. It's hot, it's incredibly deep, and yes, it's surrounded by strange life forms, meaning those of us who are completely obsessed with the theoretical math. But this topic is undeniably hot right now. It's stepping way out of obscure physics labs and into the mainstream. Just look at massive pop culture hits like the movie Everything Everywhere All at Once or the sci-fi series 3 Body Problem. They're making the strange mechanics of quantum physics endlessly fascinating to the general public. Okay, moving to section 1, classical versus quantum. Before we can truly grasp where this tech is taking us, we really need to contrast it with the computing architecture we already know and rely on. The computers we use every single day, our laptops, our phones, even the most advanced supercomputers in modern data centers, are classical computers. They operate on rigid, cause and effect rules. Everything is broken down into fixed bits, locked securely as either a 0 or a 1. It is strictly binary. Quantum computing, though, it operates in a completely different, almost alien mathematical landscape. It leverages those fluid qubits we just talked about, embracing massive degrees of uncertainty. While a classical computer has to process things sequentially, trying one solution, failing, then trying the next, a quantum system explores sprawling possibility spaces all at the exact same time. Honestly, it feels a bit more like how the human brain makes intuitive decisions, weighing millions of distinct variables at once. Which brings us to section 2. Quantum superpowers. So what can these incredibly fluid qubits actually do? Let's look at the underlying mechanics. There are 3 main superpowers at the absolute heart of all this. First up is superposition. Like we discussed, while classical bits are a hard 0 or a hard 1, a qubit exists in a superposition. It holds an undefined value, a probability of both states until it's measured. Next is entanglement, which is a profound, instantaneous connection between distinct particles. And finally, quantum tunneling. In the physical world, a subatomic particle can literally pass directly through a solid physical barrier. Computationally, quantum computers use this tunneling effect to bypass massive mathematical hurdles. Imagine trying to find the lowest valley in a massive digital mountain range. A classical computer might get stuck in a high-up valley. Quantum tunneling allows the system to just phase right through the mountain to easily find the true lowest energy state, revealing the absolute best solution. Let's dive deeper into that second superpower, entanglement, because it is massive for computational advantage. In classical computing, individual bits are deliberately isolated so the state of one doesn't accidentally mess with another. But qubits, they can be intentionally entangled. Change the state of one particle, and it causes an instantaneous change to another, seemingly faster than the speed of light. Albert Einstein famously referred to this as spooky action at a distance. But computationally, this spooky action is pure magic. It allows processing power to scale exponentially, not just linearly. You aren't just adding one more bit of processing power, you're doubling the capability of the entire interconnected system. The whole thing becomes a highly efficient, intertwined bowl of computational spaghetti. The crucial point here is, how do engineers actually control this? Well, Programmers don't just throw raw data at a qubit and hope for the best. They use deeply specialized quantum logic gates to manipulate these particles. Similar to the logic gates that route electricity in a classical chip, developers use specific algorithms. Applying a Hadamard gate, for example, officially places a qubit into that fluid state of superposition. Applying a CNOT gate is what permanently entangles two qubits together. By deliberately twisting and entangling these delicate states, programmers create a probability environment where the optimal solution is the most mathematically likely outcome when the final measurement collapses the system. But hey, welcome to Section 3, the Coherence Challenge. It's definitely not all magic and easy answers. There are massive, real-world physical hurdles to building these machines. Which logically begs the million-dollar question. If this technology is so profoundly powerful, why isn't there a shiny new quantum computer sitting on your desk right now? The answer lies in a vital concept called coherence. Qubits are unbelievably delicate. At their core is a tiny amount of coherent matter, maybe a single trapped photon or a suspended ion. To maintain those superpowers of superposition and entanglement, that particle must remain perfectly free of any outside interaction. It needs extreme, multi-million-dollar protection from ambient heat, the absolute slightest physical vibration, and even stray electromagnetic noise. If the chaotic real world intrudes even slightly, the qubit instantly loses its coherent state, and the calculation collapses into useless noise. Keeping these perfectly isolated is arguably one of the hardest engineering challenges in history. In fact, they are so fragile that engineers have to use intensive error correction. We often need thousands of volatile physical qubits working together just to create one stable, reliable, logical qubit. Section 4. Why quantum matters. Despite those monumental engineering challenges, the global race is definitively on. Let's step back and look at the tangible human and commercial impacts. We need to clear up a massive myth right now. Classical computers are not going away. For your daily emails, streaming video, or basic spreadsheets, classical machines are perfectly fine. A super-cooled quantum computer would actually be terrible at running a basic word processor. But look at the right side of this table. Quantum computers are built for monumental tasks that cause combinatorial explosions. Problems with so many rapidly moving variables that the best classical supercomputer would take tens of thousands of years to solve them. We're talking about accurately simulating the atomic behavior of a complex new molecule to fight cancer, or perfectly optimizing a sprawling global supply chain while accounting for thousands of unpredictable weather and manufacturing variables in real time. Quantum is here to solve the fundamental mysteries of advanced chemistry, physics, and logistics that were previously unsolvable. So, the ultimate takeaway to leave you with is this. Quantum computing is stepping out of academic physics and directly into commercial reality. Major players like IBM, Google, and AWS are pouring billions into the space, and they're already offering live cloud access to functional quantum processors today. Literally anyone with an internet connection can log on and experiment with rudimentary quantum circuits. From those accessible platforms to the rapid daily advances in error correction, the arc of this tech is bending sharply upward. Within the coming decade, it will entirely redefine global data analysis. The question isn't if this computational leap is going to happen, but when. And are you and your business ready to take advantage of it when the wave finally hits? I really hope this structured breakdown helped demystify the incredible underlying magic of quantum mechanics for you. If you enjoyed this, subscribe to an 8 Minutes and never miss what matters.